Hey everybody, this is Mr. Brooks again. So today we're going to cover 3.12, which is higher order linear homogeneous equations with constant coefficients. So last time we talked about the different types of solutions and how we could generate them. So we're actually going to look at a very specific set of homogeneous equations. So we're first going to consider the nth order homogeneous linear equation, y sub to the nth derivative. Again, when we put a number in parentheses, we're indicating the derivative because prime notation only goes up to 3. Okay, and so we have these a sub n minus 1 and so on. Edit here. And these guys are just these constant values that are going to happen in front of these. Okay, so the general solution would look of the following form. Y of t is equal to c1 y1 plus c2 y2 plus so on up to c sub n y sub n. Okay, here where y1, y2 all the way up to y sub n forms a fundamental set of solutions. Okay, and again, how do we determine that it forms a fundamental set? Is we take the Wronskian of this particular set, and we find out that if it's non-zero, then we know it forms a fundamental set. Okay, so let's go back and talk about, well, how do we come up with these solutions? How do we find out what y1, y2, and so on are? Well, let's look back at what we developed in section 3.3, which was when we dealt with constant coefficients for a second order linear. And so when we looked at these, we looked for the solutions to be of the form e to the lambda t. Does everybody remember that? And so what we did is we took these and we plugged them into our second order, and then we found out that, hey, when we take the derivatives and everything like that, in the end, we get this interesting looking equation multiplied by e to the lambda t, and this is all set to equal to 0. And we said, okay, well, e to the lambda t is never equal to 0, so that means this equation with these lambdas in there is what's going to cause it to be equal to 0. And so that's what we're going to be doing here. We're going to plug this into our nth order differential equation and look at what we call the characteristic equation. So we've talked about that guy before. So in our case, when we then use the solution to develop the characteristic equation, okay, and that characteristic equation I'm going to put over here is of the form lambda to the nth power plus an minus 1 lambda to the nth minus 1 power plus so on plus a1 lambda plus plus a sub 0 is equal to 0. Okay. So now what we've done is we've formed this polynomial equation with constant coefficients, and we could solve for these guys, provided that we know how to solve a polynomial equation. Well, with the second order, that was pretty easy. We had the quadratic formula to help us for everything. So if we could factor or use the quadratic formula, we could find out the solutions of these. So notice that we are going to be increasing the level of difficulty with these problems because we're going to third order, fourth order, fifth order, and so on. All right. Here, where the roots of the equation define the solution. Having the form y of t is equal to e to the lambda t. All right. So let's talk about these roots, because we are going to run into some issues like what we did from section 3.4, 35, and 36. So here, the roots of the characteristic equation, well, when we dealt with the second order, when n was equal to 2, we were able to list all the possibilities. And those possibilities were straightforward. We either had two distinct real solutions, we had one repeated real solution, and the two distinct conjugate pair, complex conjugate pair. Of the form alpha plus or minus I beta. That looks like pain. Let me change that to pair. Define that R a little bit better. All right. Well, that's great if we're dealing with the second order and we know how to deal with those guys. Well, to generalize this would probably be an impossibility to talk about all the different ones that we have. So we're going to make a couple of observations here. The first observation, so this is where the two main cases is coming from. So the first one is the roots, and we're going to call those lambda sub I, just to say that we have an I amount of them, are distinct. Okay, so that could mean they're all real numbers, or they're real roots. And if they're real roots, we automatically know what we're going to do with those. Just like what we did with distinct real roots, we're going to do the exact same way here. So these guys are going to be of the form y of t is equal to e to the lambda t. So just like what we talked about our solution over here. Now, if they're complex roots, that's where we've got to change things up a little bit. So complex, so if we find out that they're distinct, but then we have complex conjugate pair roots. Of the form alpha plus or minus I beta. These guys were of the form. So if we had just one set of solutions, so if we were dealing with a second order, we'd get something of the form y of t, we'll say y1 of t, is equal to e to the alpha t cosine of beta t. And the other one would be of the form y sub 2 is equal to e to the alpha t sine beta t. Okay, and that's the nice thing about this is complex numbers always, when we're dealing with roots, they always come in pairs or conjugate pairs with each other. So that is the nice benefit of this. So once we know one, we do know the other. So there is that benefit to this. All right, so the other one, the other case that we would look at is that the root is repeated r times. So notice that this one is more likely going to be the case in a lot of situations because we could have two repeated roots and then the rest of them are distinct. So we'll have to go with that particular style here in just a second. The nice thing is we can mix these in with each other too. So if we have distinct and we have some repeateds, then we can intermingle with them. And that's kind of what we could do here, except we only have one repeated real solution with a it is equal to 2. So in our case, another way to write this, so if the root is repeated r times, that means that the characteristic equation, so in other words, the characteristic polynomial has the factor of lambda minus lambda sub I. So this is just some value here, and then it'd be raised to the r power in that case. All right, so the next step is, well, what do those solutions look like? Well, remember, once we found one of those repeated factors for the quadratic, We found the other solution by tacking on a t to it. And actually, we're just going to extend that idea out. So if we have a real, so this is 2a, okay, going with the repeated roots. So if that's the form, if they're real, repeated roots, these guys would be of the form y1 is equal to e, so I'm just giving an idea here, lambda 1t. y2 would equal t e to the lambda 1t. y sub 3 would equal t squared e to the lambda 1t, and so on, up to y sub n would equal, y sub r, and again, r here is the number of repeats that we have, is t to the r minus 1. Okay, so notice here, when we had 2 of them, we only have t. When we have 3 of them, we have t squared. So when we have r repeated roots, it's t to the r minus 1. E to the lambda 1t. Okay, so just to give an example, real quick, if we found out that lambda 1, or lambda, was equal to 3, and it's repeated three times, our solutions would be of the form y sub 1 of t would equal e to the 3t, y2 of t would equal t e to the 3t, and y of 3 of t would equal t squared e to the 3t. So notice that it's just that simple of the substitution in there. Okay? So the next one is, well, what happens when we have complex numbers? Again, this is part of 2a where we're having the repeated. So let's say complex conjugate pairs. Again, here lambda 1 and 2 is equal to alpha plus or minus I beta. Okay. Well, they would be of the form y1 of t is equal to e to the alpha t cosine of beta t. y2 of t is equal to e to the alpha t sine of beta t. And now we're dealing with the repeated. So once we get these conjugate pairs, and then we notice that they are repeated, then these guys would be of the form y3 of t would equal t e to the alpha t cosine of beta t. y4 of t is equal to t e to the alpha t sine of beta t. And they would repeat this pattern for n number of repeats. Okay, so that's it for what we're going to be discussing for part 1. It was just laying down the foundations. And in the next video, or the next segment that we'll have here, we're going to go over just a bunch of examples to show you exactly what we're talking about. All right. All right, so we're back. This is part 2. Okay, just giving you a bunch of examples to go over. So in this particular situation, what I'd like for you to do is, if you are wanting to work this out on your own, so take a second, pause the video, and these are 3 examples that we'll be going over. So just again to talk about it, so that way you can see what the values are. We have a 4th order y to the 4th derivative minus 5y triple prime plus 6y double prime is equal to 0. Our next example is going to be y triple prime plus y double prime minus y is equal to 0. And our last one, which is going to be a fun one for us, and notice I left a lot of space, so I would do the same thing for you guys, is we have a 5th order, so we have y to the 5th derivative minus y to the 4th derivative plus 2y triple prime minus 2y double prime plus y prime minus y. And we're going to talk about this one a little bit more in depth of what we're going to get into. All right, so now that you're back and after you've paused and worked these guys out on your own, and I know you guys did that, right? Let's go over this one. So first of all, let's find our characteristic equation. So this is really nice. It's the exact, almost carbon copy of what we did in 3.3 when we're dealing with those guys with second order linears. So all we do is we say, well, this is lambda to the fourth minus 5 lambda cubed plus 6 lambda squared is equal to 0. Well, we can solve this guy, okay? So notice here, every single one of these terms has a factor of at least a lambda squared in them. All right, so let's factor out a lambda squared. So we have lambda squared times lambda squared minus 5 lambda plus 6. All right, and this is equal to 0. Okay, well, can we factor this further down? Well, if I have a negative middle term and a positive end term with a quadratic, if I can factor it, it means both factors are going to be negative. So here, I'm just going to copy this down one more time. So what are the factors of positive 6 when added together give us negative 5? Well, that means it's negative 2 and lambda minus 3. Okay, and again, just to double check that, we add these two guys together, we're going to get negative 5, multiply them, we're going to get positive 6 out. All right, so notice I get lambda squared is equal to 0, lambda is equal to 2, and lambda is equal to 3. Notice we have a repeated value here. So our solutions, or our general solution, is going to be of the form, well, remember, these guys, when we're dealing with real roots, is e to the alpha, or to the lambda t, okay? So when I plug in 0 for the first time, I'm going to get e to the 0 times t, which that means I'm just going to get e to the 0, which is 1. All right, so that means I'm going to get out a constant value for that first one. All right, plus, now dealing with the repeated root, okay, if it's repeated, we tack on a t to it. Well, this means this is going to be c2t. Okay, so this is how we're dealing with this repeated root here. All right, and now the other guys, since these are distinct from the repeated, these guys are just c3 e to the 2t plus c4 e to the 3t. And that is our general solution to this homogeneous linear equation. All right, so make sure that you got that. Now it's okay if we have this, you have this one here, or if you wanted to move the distinct ones up front, that's perfectly fine. Again, these are arbitrary constants, so the order does not matter in this particular situation. Okay, just make sure that you're dealing with the repeated 0 here. Okay, next one. All right, we have a third order. This one is not too bad. Factoring is going to be a pain in the butt, but let's see if we could use factoring by grouping. So typically, if I have a third degree polynomial, I'm going to try factoring by grouping to see if there's something in common I could pull out. If not, there is another way, which we'll talk about in the next example, of certain techniques you can try with these guys. And it's going to involve, I'll go ahead and warn you, synthetic division over there. All right, so with this one, again, write out your characteristic equation. So we get a third order differential, or third degree polynomial out of this one. So I'm going to factor the first two terms and factor the second, or group the first two terms and group the second two terms. All right. So if I keep that minus out here, we got to make sure that we change signs. So be very careful of that. This is where a lot of people, it's a simple mistake that can occur, is if you leave that negative on the outside. I've seen a lot of people leave this negative on the inside, which is a big no here, because you are distributing this back. So you will be changing the problem. So make sure if you keep that negative on the outside that you do deal with every single sign change that occurs with that. All right, notice that these guys have a lambda squared in common. So if I factor that one out, notice I get a lambda plus 1. Well, if that's the situation, notice that both of these are in common. So if we treat this as a one particular unit, we get lambda plus 1 times lambda squared minus 1 is equal to 0. Well, notice, if I factor this further down, I am going to get lambda minus 1, lambda plus 1 out of this one, and a lambda plus 1. So notice I do get a repeated root out of this. So therefore, I have lambda 1 is equal to positive 1, and lambda 2 and 3 is equal to negative 1. Okay, so I have a repeated root. So therefore, my characteristic, or my solution to this is going to be of the form y of t is equal to, again, remembering the form of our solution here. So y sub t is going to be equal to, I'm going to deal with my distinct one first, of c1 e to the t plus c2 e to the negative t, because I'm dealing with the first one. So again, that's the nice thing, is even if we have repeated, we're still going to have at least one of them that doesn't have a t out in front. And now dealing with, all right, so that's our solution. Moving on. So this is a doozy of a problem, but it's not too bad, especially once you figure out a couple of techniques for this. So first of all, let's write our characteristic equation. So lambda to the fifth minus lambda to the fourth plus 2 lambda cubed minus 2 lambda squared plus lambda minus 1. Okay, I'm just double checking myself and make sure I have wrote this correctly. All right, so factoring by grouping is not going to help us in this situation. Factoring would be great if we could do it. So Rene Descartes came up with a way to come up with, if it does have a rational solution, then it would be the quotient of the leading coefficient and the constant at the end. So that means 1 or negative 1, in this case, because our leading coefficient is 1, 1 or negative 1 could be a possible solution. Not necessarily that it is 1, but it could be 1. All right, so remembering synthetic division, I'm going to put my root of 1 in here. That means that would be a factor of lambda minus 1 in that case. And then you write out the coefficients in front of each of these values. So 1 minus 1, positive 2 minus 2, positive 1, negative 1. All right. And then you bring down your first value, and then you multiply. Well, 1 times 1 is 1. And then you're going to be adding these rows. Well, negative 1 plus 1 is 0. 1 times 0 is 0. So we bring down the 2 when we add those. Then 1 times 2 is 2. We get a 0 out. And then 1 times 0 is 0. We bring a 1 down. And 1 times 1 is 1. And that means we get a 0. So with synthetic division, if you have not seen it in a while, when we get a 0 at the end, this means this is a root of the original. Okay? Now you could test some other values out, and that's not going to really help you in this situation. The nice thing is we actually have our new equation out of this. Okay, our simplified one, once we've taken this factor of lambda minus 1 out. But that's the really cool part about synthetic division. What it does is it reduces our polynomial by 1 degree. So this is lambda to the fourth, 0 lambda cubed, 2 lambda squared, 0 lambda plus 1. So this is coming from these coefficients. Again, this is the fourth power, third, second, first, 0 power. Okay? We still want this to equal 0. Okay? So that means, well, this looks like a quadratic. Even though it's a fourth degree polynomial, we can still deal with this guy. All right? So this is lambda squared plus 1 times lambda squared plus 1. Well, another way to write that is lambda squared plus 1, the quantity squared, is equal to 0. So notice that we're going to have a repeated root here. We'll also notice what that generates for us. This is a what? Well, that is going to is a sum of squares, which there is no solution for this if we're dealing with real valued numbers. So this lambda squared is going to be plus or minus I. And notice that this happens twice. So we get this pairing of happening twice there. And we also have our lambda is equal to, and so I'm going to say this is repeated twice. Or multiplicity 2. And then we also have a lambda that's separate from this that we use in our first. So don't forget about this guy. Okay? So otherwise you would only have 4 solutions when you actually have 5 solutions for this. So notice there that the number of solutions has to equal the number, the degree of the polynomial in that case. Okay? And notice here that we had a 4th degree, we had 2 zeros, a 2 and a 3. We had a 3rd degree, we had a 1 and 2 negative ones. Okay? So, that being said, if we're repeating it, let's deal with the real root first because that's the easier of the two. So y of t is equal to c1 e to the t. That was our easiest one. Now we're going back to, well, if there are complex numbers, remember these guys were of the solution, e to the alpha t cosine of beta t, and then y of t is equal to e to the alpha t sine beta t. All right, well notice here that our alpha is 0, so these e to the alpha t's are going to go to 1. And so that means we're just going to have sine and cosine. This is dealing with that first group. Okay, so we're going to get plus c2 cosine of t, because our beta here is 1, plus c3 sine of beta t. All right, and now we deal with the repeated. So we dealt with the first group, now we're dealing with the repeated, which means we need to multiply these by t. So we're going to get plus c4 t cosine of t plus c5 t sine of t. And then that is our general solution to this homogeneous. Okay. And if we had initial conditions, we could then plug those values in and solve for C1, C2, C3, C4, and C5 for that. But notice, if we have a 5th degree or a 5th order differential equation, we'd have to have 5 initial values for this to solve for these guys. So notice that the intensity of these problems does build up, and that's okay. We can deal with those. So the big thing here is setting up the general solution for these. Right? And so that actually ends 312. So this is a very relatively fast lesson to go through. So again, take your time through this, and I will be assigning a homework to go with these as well.